Welcome to this Frequency Matters podcast. I'm Pat Hindle, and I'm here with my co-host, Eric Higham. Today, we're talking about the future of cellular communications with Emilio Calvanese Strinati, Smart Devices, Telecommunications, and Security Strategy Program Director of International Research Programs at CEA-Leti. So, Emilio, you've been involved in many research projects in the area of 6G. Can you tell us about the EU partnership efforts for 6G?
So we actually, in the last call from the European Commission, the SNS joined a GU that was actually added in 2023. There were several projects proposed under the umbrella of wireless communication and signal processing. And actually, we have been proposing a couple of them that have been accepted. One is 6G DISAC, which actually is focused on 6G for distributed intelligent sensing and communication. And the other one is 6G Goals, which is focused on semantic communication and goal-oriented communications. The first project, 6G DISAC, mainly is focused on a distributed system where you have integrated communication and sensing. So you integrate these two functionalities normally always been separated. Actually, is also one the hot topic in 6G research. And actually, the project also really looking for concrete advances in a way to impact in the standard compatible solutions. And it challenged many aspects of the current vision of 6G, like, for example, how we do tracking of user devices, how you do tracking of passive objectives, how we do distributed actually function that already in study about sensing and communication, and also in general how efficient we do signal processing on the systems. And actually, there's one ingredient that's really making a difference, and there's two ingredients actually making a difference in this project. One of this is that we go for a distributed system, which do not have a centralized architecture, and actually we enable different functions to coordinate together in a distributed fashion. So actually having a system which is scalable and very flexible. And the other ingredient, which actually is extremely novel, is the use of semantic communications. And that goes actually in the direction of exploring new avenues for fusioning data captured by sensors, not only at the data level that we capture from the sensors, but going to their semantics and the meaning they can make for the receivers. This actually unlock new avenues of research that we will explore for the next 3 years. Then on the 6G Goals project, we actually, this is the only project been accepted in the call, which is completely, I would say, future looking and disruptive in a way that it's really going one step ahead in looking for the future. Something might be not impacting directly the first generation of 6G. It's really for it's also establishing the future, and it's focused mainly on the inclusion of artificial intelligence natively in a 6G system. And actually, what we do here is that when artificial intelligent machines and reasoning engines are exchanging within them, they do not need to use the same way of exchanging data as we did in the past, because they have the ability of interpreting the data and extracting knowledge and formalized knowledge out of that. So what the project is doing here, the 6G Goals, is to apply fundamental principles that have been proposed 70 plus years ago, but actually never explored, on how to reshape completely the communication system when artificial intelligent machines are exchanging between them. And there are many challenges there. First of all, either just the definition of what is a semantic communication system still today is an open issue of research. So that's the reason, because in the second project, 6G Goals, most of the balance is in fundamental research and pre-standardization efforts. Both projects actually have a very extensive approach in terms of demonstration. So the first project, 6G DISAC, has 5 major proof of concept we'll deliver in order to show really the impact and the potential of the funding of the project, going for many types of applications. The main one we're gonna work there are about positioning and localization, and the other one is all related to autonomous vehicle and what we call in the community the link prediction, and actually showing and understanding really how an autonomous vehicle can understand about which is the environment, which is the context where it will operate in, and have to decide and control. On the contrary, on the second project, CG Goals, focused on this semantic goal-oriented communication, the major work or demonstration will be in terms of collaborative robots. That means we will consider a swarm of different robots that have to collaborate together, and instead of using the classical way of communicating, they're changing semantics with a defined goal for the communication.
Thanks, Emilio. That was a great answer. Integrated sensing and communication are a key objective for 6G. Can you tell us how this works and what are the challenges to achieving this?
Yeah, thanks for the question. That's important actually to see that the idea of integrated communication and sensing is really to embed these two functions. One is the communication, the other is the sensing, in the same communication attempt. So actually, let's consider when we do communication, we use a waveform delivering the bits that goes over the air. And actually, in these waveforms, in the same time, we send actually the communication act, so the information we want to send, but we also include the thing that we are able to actually censor and measure something in the environment. This actually requires to rethink about how we engineer the waveforms. And one of innovative part actually in the CG DISAC projects, really we not only go for an engineering of classical waveforms, but we also use the semantic approach, for which we completely change the way of how we shape and define the constraints for these waveforms. There are many challenges around that. First of all, it's really the challenge of enhancing the communication performance that in terms of latency, in terms of throughput, in terms of reliability, but also in terms of scalability and distributed resource allocation that actually are, from our perspective of the CG DISAC project, enabled by actually distributing the architecture, enabled to avoid to have a centralized unit, but so indeed having different agents, different functions that cooperate together. Then there's the other big challenge is that about how efficiently we do processing on large volumes of data, particularly when we use multi-sensors and multi-target scenarios, and also those multi-sensors might be completely heterogeneous. Because actually, if you go for what we classically do today with data fusion approaches, that can be somehow complicated in terms of implementation, and most of the time either not very, I would say, effective in terms of the way to be implemented. Here again, we have these two ingredients of the distributed functions that actually enable to do processing in a distributed manner. So also leveraging from different partner next they might have either the skills to do the processing in the specific way, so indeed the hardware, for example, and the availability of the resources there, and either maybe the energy, the type of energy available to be fed actually to this processing unit can be of kind of more sustainable, greener, and so on. And the other ingredient, which is very important as well, is about, again, the semantic part, where actually instead of doing classical fusion of the data, we do this fusion at the semantic level. So instead of fusion the data itself, we fusion concept and relation between concept. And actually we create a complete different understandable way of fusion that is much more digestible for AI algorithms that then will work on that. There's also another challenge is to define the theoretical guidance for the design of minimal resource consumption strategies in the sensing, and also which is the minimum information sharing we need for a specific goal. So because we are fusioning different sources, what is the minimum amount of resource we need change? And this actually is very open question in research today.
Integrated sensing and communication are a key objective for 6G. Can you tell us how this works and what are the challenges to achieving this?
Yeah, well, thanks. So first of all, about which are the capabilities we actually unlock somehow. I would say that the first one, very obvious to understand, which actually is also one of the basic important one, fundamental one, is actually the context awareness that we enhance, and also we can provide in more real time in their update. So actually what you do actually here with the joint communication and sensing, we gather rich contextual information from the environment, such as the localization, the movement, the environment condition. And then we can build kind of a dynamic radio map environment that we can use then when we do optimization of our system. Then I was saying before, also this improved data fusion with these multimodal and heterogeneous sources, actually, and one of the things that we see as really pushing this approach of the semantic way, pushing this approach of the distributed system, which actually can check and decide how to fusion from different kinds of sources. Then we have also the real-time decision making and control. That is really a new capability we can do it here. It's actually we make use of reliable data because actually of this updated context awareness, because of this improved data fusion, but also ultra lean information we can gather. We actually, if you take the semantic approach, for example, we can really extract to the essential information is needed for the specific task and accomplishment. Then you have, in general, say what we can call adaptive communications. As, for example, adaptive modulation coding schemes, adaptive number of antennas, in either adaptive resource allocation and orchestration. That's also is improved because we are giving more contextual awareness, more real-time contextual awareness. And now we also have this increased efficiency overall, because actually we share spectrum among different functions like communication, computation, sensing, and also we share the infrastructure, again, able to do the communication, the computation, and the sensing. And this actually is expected to give a very notable cost saving and improvement of performance on both CapEx and OpEx. And then about the applications, I would say that there are many families of applications that involve sensors in general. Let's say, just to name a few, smart cities, everything that's about, this monitoring and automation and control of a system, a large system, autonomous vehicle and smart road infrastructure. Also, Industry 4.0, or maybe if we also start thinking about something it will be called in the future 5.0, where actually we also have this native integration of intelligence. The environment monitoring in general, that can be also beyond the boundaries of a smart city, and the collaborative robots, collaborative drones, collaborative fleet of autonomous entities. I would say those are mainly the application, I would say.
You've mentioned semantic a couple of times. Can you tell us about how emerging AI and ML-based architectures could offer semantic and goal-oriented communication systems, and what that means for the user?
Yeah. So about architecture, it's really something. It's something ongoing in the way that actually the basic architecture is the AI native architecture for 6G that actually has just been started under discussion. So it's something new. And what happened here in the architecture as a change is that actually we need new planes of interaction, so new layers in which we have discussion specific for AI. So what we call here is as what we call the semantic plane, where actually we can understand and communicate and adapt if errors come into the communication are not necessarily due for the classical wireless communication noise we have, but maybe because there are the two intelligence engines there, or the intelligent agents that are interacting to each other may have a mismatch logic, so they do not reason in the same way. Things, for example, they're not using the same language, or have not been trained on compatible data sets, and so on, for which either if the message is completely perfectly received, doesn't mean the same thing from the transmitter and the receiver. So all these things actually put a challenge about the architecture, and one of the promising approaches really explore what we can do with the ORAN architecture, and then we are exploring in this project, for example, the inclusion of what we call a semantic RIC, a semantic radio controller. Yes, and then about the advantages, I wish separating two advantages. First of all, is an indirect advantage for the people, for the users, which actually is the advantage of a more effective network functioning. And actually, what we really want to achieve with semantic goal-oriented communication is to define an efficient AI native zero-touch networking. That means actually we do automation and deployment and configuration and management of the network infrastructure without human intervention. And actually, again, it's because we are considering that the elements that are exchanged to each other are not necessarily human beings, but actually a machine that have their specific way of reasoning. And then the advantages for the humans are, I would say, first of all, a natural interaction with the AI interfaces and cyber physical systems. Let's consider, for example, interaction we might have on the metaverse. Then also an enhanced understanding of machine on human interest and intent, does actually do more personalization of the service and also optimize the performance for a specific typology of need for the user. Yeah, I would say that these are mainly which are the major advantages. Of course, the other advantage is that we are sensing less, communicating less, and indeed we are stressing less the network. That means we are consuming less, and in principle, we want to see how much we can enable sustainability in the network and the service.
So Emilio, it sounds like some very ambitious undertakings here. What's the time frame, and what do you expect the results to be for these projects?
Okay, so both projects has kick off on the 1st of January 2024 and will go on for 36 months. So this is the time frame. Actually, is a perfect time frame for 6G because it's a period in which we are still exploring and considering new functionalities, and we start seeing actually how those can be included in the standard, and for which the proof of concept are very important in order to selection for this last phase of the standards. And actually, what we are expecting as a result, so I would say I would like to divide the two different projects. For 6G DISOC, I would say we are expecting really to impact standardization, because actually the ISAC, intercommunication and sensing technology, is some kind of in this first stage of maturity. So it's not finalized yet, but there's already a consensus on understanding and some already known here and there functionality that already exists. And what we expect to do is to really, through our proof of concept, our 5 proof of concept we're going to deliver, to showcase different functionality, how they work, and that can be somehow performing in a CG system. And then with the 2 trials we'll deliver, also see how orchestrate this different of this function, how we can improve overall the system. And one a very huge expectation I have personally on this CG DISOC is the first ever, attempt of defining semantic aware waveforms for ISAC with a demonstration based on lab demonstration to see in real, in emulated real CG channel propagation context, how actually they can perform and how much we can reduce in terms of number of amount of data we have to share, and how much we can improve the reliability. For the CG Goals project, which is focused on semantic goal-oriented communication, I would say that this is a different approach. We are in the pre-standardization phase. So the idea is not necessary to impact directly the standard today, but to give the background for a next stage of standardization. But still, there's one expected result is the definition of the semantic aware architecture that actually will impact the today discussion on AI native architecture for 6G. And then actually other expectations are, of course, to really lay down the theoretical background and the major key foundational ideas about what CG communication should be, how it's different from other concurrent technology that, today there's some misconception. We want to clean up these misconceptions. And then at the last phase, we have these important trials of cooperative robots that will show how, including some algorithms and new techniques and semantic oriented communication, we can really have an ultra-link communication between robots that collaborate to do a specific goal together, going together in a specific space, move as a team, a specific object, localize some object, some people, and so on.
Well, thanks, Emilio, for taking the time to talk to us about the future of communications and research being done towards 6G. That was good information, and we thank you for your insights today. And to our listeners, you can find more podcasts at podcasts.microwavejournal.com. And thanks to everyone for listening.